Okay. Everything seems to be in order. Maybe. Not sure. It's going to be a quick one. I mean, I am not going to do too much besides just maybe testing the first environment. Actually, the setup of this capture software was a little problematic. Also was caused because of the new version of Linux. Doesn't matter right now. So I know that maybe nobody is watching me right now, but for the ones that don't know me, I am Christian Duran. I am a PhD student from the University of the University of Santander, maybe. I don't know. Universidad Industrial de Santander is in Spanish. Yeah, from Colombia is, but right now I am in Japan. So I have accumulated quite an experience with RISC-V, and I want people to I want to share with people, because most of the time the people doesn't know how to actually integrate those kind of systems. There is a lot of people trying to see how it works or see what it happens. And yeah, in this channel you can also see maybe some tutorials also in Spanish, or also some games, but no. The thing is that I have seen a lot of people struggle with this. But right now I'm just going to go ahead and try to explain you what to do to implement a RISC-V system. And the way that we are going to implement this RISC system, I am not going to show you how to build it from beginning to end, like each thing, each line of code, each line of hardware. No, not that kind of thing. But rather maybe use another kinds of hardware, trying to put it all together and set an environment to do a RISC-V integration. And the RISC-V integration is going to have like a processor. For example, I'm going to use the Rocket chip, or maybe another processor. It's irrelevant. And on that processor, we are going to run software. My objective is to actually make a RISC-V console. I mean, yeah, there's like a game console or something that plays games, something like that. Because in my opinion, there's a lot of boring stuff happening. In my opinion, myself. Happening in the RISC-V environment. So often the people just treat RISC-V like this business, or maybe this serious coding style, and they're trying to make it free and that kind of stuff. And there's a lot of people that are implementing these kind of things, but that's not the way that's not what I'm going to discuss there now. And that is not the way that we are going to do that. So we are going to just use whatever that is in the whole ecosystem and try to implement something like that. The final objective is like that, but no, it's not going to have anything there. This live event maybe will be only some minutes long, maybe half an hour. We are just going to just run some tests. This is actually a test. I don't expect anyone to see this. So let's get started. So the first one, I'm going to go to some random folder. I'm going to create just this project. So to choose this name, I'm going to name it RISC-V console, something like this. Something silly. It can be named project. I don't care. So what we're going to have here is any kind of processor that is going to be inside here. So my suggestion is to actually have chipyard. Chipyard is a pretty nice project that implements a lot of cores and melts together to make a mega chip or any kind of chip there. We can use that as a starting point because this has a lot of things. And if we want something smaller, maybe a PQRB or maybe a server or maybe a whatever, we can start from there, or maybe just discard it together and put another SoC. In my opinion, Verilog for Verilog only design is going to be a little difficult to understand. I don't even understand my own comment, my own code. So I'm going to clone this. So git clone https maybe github.com/ that is UCB bar, no? UCB bar and chipyard.get. Let's see if it works. Flawlessly. So I always recommend the people that actually works with me that try to follow the instructions. For God's sake, please follow the instructions. So what I'm going to do is let me just bring this here. I'm going to no, I don't know. Go to the chipyard repository, and there are some neat instructions here that you can follow. Okay, they are not here; they are in the documentation. So chipyard, read the docs, and there's some chipyard basics here that you can just follow. But what we are going to do is setting up the chipyard repo. So you clone it like I did it, and then you run this. The init some models now RISC-V tools and something like that. So we are going to just do that. So chipyard, and we have here this catalog of stuff. I think I have my RISC-V environment variable ready. Maybe okay. That is echo RISC-V. No, it's not set, so I'm going to set it. I have it. Globally installed. Is RISC-V is equals to opt RISC-V 64GC. There's the tool chain and some other things like the ISO simulator. Some things there. Yeah, it's not important. Well, it's important to set up this thing. So we're going to run this, but we're going to say that we don't want Firesun because I don't have money for a Firesun right now. Yeah, that is a cloud thingy, FPGA based simulation that can accelerate the simulations for this particular kind of chips that they are doing. They are trying to do this for rocket for very big RISC-V very big RISC-V processors like the rocket, like the full rocket and the boom. And there's another ones there. So right now it just copying stuff. It's going to take a while. But let me brief you what is inside of this chipyard. So actually this chipyard, what the hell? Maybe this one. Yes. Like I told you before, it's just a chip builder. So the way that this chip builder works is that it generates the hardware. That means that generates like Verilog files, but not only generates Verilog files, it generates like as long as I understand, it's a lot of like the DTS, like documentation about your or documentation sheets that you can use for documenting your hardware. And this is intended to be maybe multi-platform, so you can. The intention is to run it as a simulation, and run it with a FPGA accelerated simulation using Python. And the other one is to actually do it with VLSI. I haven't touched the VLSI run of this chip yet, but it's not like I can do it because maybe it's an internal thing from this university, the University of California, Berkeley one. I don't know how that works. Whatever. So yeah, it has the question of why chip year and why not to go with the actual stuff. For example, going to Rocket, to the Rocket chip directly, is because I mean, yeah, we can grab the Rocket chip, but then it's only going to have the Rocket chip. And if you want, for example, no, I want to implement this, I want to implement the hotshot, I want to implement the boom, I want to implement the Ariane core, that is not anymore. I think they are replacing it with the CV6. That I think it's the same actually. Or no, I want a pole platform there, or whatever. All the utilities and all the stuff is already is already done. Integrated all together in ChipYard, but we are not going to use ChipYard in the usual way. My intention is to do a similar thing like I did in the T hardware. By the way, my GitHub. I mean, sometimes I push to this using Hanken, but my GitHub is this one. CK2, what the hell? CK2, yes, this one. I have some things here, just previous project that I tried to do, but always fails because I am too busy to actually doing them. What else? So yeah, it's a similar thing that we did in the T hardware repository. This repository is still not able to be public. It's a shame. But what I basically did is to make a system on chip that can do cryptographic functions. It's not that difficult. But because it has the rocket chip, it has the boom, it has the whole thing, we can just put it all together inside there. And then we are going to do a similar thing, because for this console that I want to make, maybe I am not sure which kind of RISC-V is better, and maybe we need a microcontroller for some things, and other things are not, they are not needed. Yeah, that kind of stuff. So it should be finished, yes. And we are going to just do a test. So to run this test, we are going to just run a simulation, a very later based one. It's not going to be a super exciting or anything. So sims go to very later, yes, and we can just do make here, and this is going to make the default stuff, as long as you set the RISC-V environment, and also you set what else, and you have Java in your environment. This is going to just run, because I already run this chip year before. Is not going to have is not going to download a lot of things, but in your case it's going to download a lot of things here. For me, it's just compiling. First, it will compile the FreeRTL, then the chisel, then from there is all the dependencies that chipjar has, and this will generate a very later executable that you can run executables with. RISC-V ones, RISC-V executables is kind of the same as the RISC-V is a simulator, the spike. So in the meantime, maybe I should run a test or something. I mean, we can. It's just that doing the actual software is kind of a mess. Software is was the problem. I have seen that actually the hardware is starting to be not the problem to actually try and test those things, but actually the software is the problem. But for example, in some lesson before afterwards, we are going to do, for example, the hello world. For example, print a hello world, but printing just the hello world is going to be a whole mess because there is a driver there that is named the HTIF, and it's going to have a lot of intercommunication there that even myself I don't understand fully what HTIF is about. I know that there are two variables there, and when you do a request and you receive a response using those two variables. And the driver is written around. There's a lot of people that are written there. There's no actual documentation about that. And that's the reason I am doing this kind of stuff here. It's because there's no documentation at all of anything about this. I mean, it's free. I mean, it's free as in free in not free beer, but free in you can grab the code and do whatever you want with that code. But because it's so new, documentation is almost none. But what can I say? In ARM is the same thing. I mean, there are documentations, but those are typically long enough manuals that you can't even understand at all. Yeah, something like that. So in our case, I'm going to clone another project that is going to be the RISC-V is a simulator, and we're going to test we're going to do also the RISC-V is a test. So I'm going to refresh my memory which one is one. So RISC-V is a sim, I think is the one. Yeah, RISC-V is a sim is the first one, and the second one is RISC-V is a test, something like that. No, it's RISC-V test, I think. Yeah. It's this one. Yeah, this one. Yeah, it's this one. So the RISC-V sim is going to be the first one, but in order to test this hardware that is compiling right now, we're going to need actually this is not big enough, so this is https github.com/github.com/RISC-V is sim. That's good. And now the other one, that is the RISC-V tests. That's good. And the RISC-V test, it just carries a lot of tests there that test the ISA by itself, and nothing magical about that. So I wonder if I already have the spike simulator. No, I don't have it. Not at all. Okay, so when I do RISC-V the ISA sim, is going to have it's going to build the RISC-V ISA, the RISC-V simulator that is named Spike. So this, when you do it like this, I mean, I already have the device tree compiler. You do this cd build, and you do just configure make. Okay, but configure prefix is RISC-V. That is with this one, yes. But I forgot to set the RISC-V in this environment. So export RISC-V again. The RISC-V 64 GC. Right, RISC. This is not RISC. This is RISC-V. And then again configure. Configure prefix equals RISC-V. I wonder if I need the RISC-V PK also. Hopefully not. Oh no, it's not needed because the FSBR is here. Usually the FSBR was a dependency, but it was embedded inside of the RISC-V proxy kernel, as long as I'm aware. But right now it's inside of here. It's inside of the front end. The front end server is just inside, so it doesn't need any extra dependencies. That's good. Otherwise, we need to compile first the proxy kernel. That the proxy kernel you are going to see that it's just a library or a executable, whatever you want to see it about the stuff. And yes, this is compiling. Maybe you can hear my processor screaming. That is doing a lot of things. And this one is running. I should run the other one as well. I mean, we have cores, maybe. RISC-V tests. Okay. What about the instruction about RISC-V tests? RISC-V tests is just clone. You go recursive. You do autoconf. Git configure. Make it stop. Okay. I want to do that. Okay, autoconf. Shit. Conf. Okay. /configure prefix is equals to you know, screw it. No. I'm not going to screw it up. Export RISC-V equals to opt RISC-V 64 GC. Configure prefix is equals to RISC-V target, and then make, because I don't have it. You need to have the to this compiler to work, your compiler that you did before. I'm not going to introduce that here. The compiler that you just compile, you need to add it to the path. So I have this little thing that is named .riscv.sh that it makes me for me. We can just see it. With I don't know. That is user local bin, and this thing. Where is it? I don't remember. riscv.sh. Yeah, it's pretty basic. You are just adding path to the path, your compilers. So I have here my GC, I have here my 32IN, and I have here the Linux one. You compile it, you put it in whatever place you want to place it, and from that and onwards, that is going to be your RISC-V folder. So you put RISC-V in this one. Most of the projects on RISC-V uses this RISC-V environment. Okay, we have the RISC-V ISA test. Now we are waiting for the ISA simulator, the spike, and we are waiting for this one also. So it says here that that FSBR is not there because we have, okay, it's stuck at the simulation stage. This is easy to solve. We need to add this into the RISC-V folder, maybe, probably. If not, is an include stuff. Yeah, it's using OPT64 include, so it needs to be there. So it seems like you need to have the ISA simulator before this one, or we can just copy it. It's not that easy. It's not that difficult to fix. So it is the RISC-V ISA sim. So the FSBR is here, and everything about the FSBR is here. So you can just copy all the like MKDir, OPT RISC-V 64 GC, include and FESVR. Perfect. Then copy CP all the H files to that specific folder. Enter. And that is just enough. I mean, I'm going to check it again. It's there. Okay, I'm going to run this again. It's not supposed to run all the stuff. Okay. So config.h is not there because I am stupid. Okay. Maybe I needed the proxy kernel. Okay, maybe it was the proxy kernel. RISC-V PK. I also know that the proxy kernel has a definition of the FSBR. Maybe I'm wrong. Not sure. No idea. We can just copy that config.h. I mean, it's not going to be dangerous as long as it doesn't exist there. Let's see. No, it's not this one. So in include there is a what? Config.h. No, so we can just copy it. Okay, it's in build config.h. I wonder if I install this RISC-V thing, it will copy also that. That would be useful. But in the meantime, I'm going to copy it because we are doing this because this is not finished yet. Yeah, don't be mistaken. I know the way that is done. RISC-V 64 GC include and that thing. Okay, and now it should run. Sure is a bold statement here. Okay, it's passing. The reason why it needs that FESBR is because it uses the same protocol that is for interacting with the console. I mean, it's not precisely the console, but the way to interact the hardware with the software. if the simulation is a software is a software CPU like the one that we are doing here. I mean, when you are doing a simulation of a core, you are doing a soft CPU, software CPU. So pretty much it's like that. Same for this one. So I think I can do here make install, and that should be enough. And yes, it includes the FSBR stuff that I told you before. So it copies whatever it needs to there. So yeah, in order to have the chip you're working, you need to have the ESA simulator previously installed. I had installed it before, but I moved the folder because I updated my GCC to version 10, so that's why there is no RISC-V ESA here. So the way that this works is that you can run this ESA simulator with the same software as this one. That is the way that you do it. So for the time being, I'm going to go to the RISC-V 64 GC. And this it's not installed yet. Make install about the RISC-V test. So this is going to be the target, the share, the RISC-V test, so the ESA. And if you want to run the ESA or you want to run the benchmarks, is there. All of that is there. So this processor supports everything, but we can just run the one specific instruction, like this one, for example. Or if you want to run everything, there is a full full one, but I don't see it anywhere. Maybe I'm just old and and this utilities just change. So for this one is a spike. Okay, I don't have it here. RISC-V spike, a spike, and the name of your executable, and it did like that. It runs a test, and it puts here. I don't know why is logging. It's not supposed to, but it's there. And it's running and it's doing something, but it's not supposed to run like that. Help. Maybe we should disable that thing. It's the PCs, the hard IDs, log cache extension. That means that it's in the debug version, but we don't want the debug. I don't want the debug. The debug is bad in this situation. I know that it's running, but but it's definitely not doing what I want to do, because it's just running. This is what is meaning. This what it means is that for each instruction is saving this, or in this case it's not saving anything, but it's reading this too, and the next instruction, that is whatever is here. It saves to this address something, and yeah, that kind of stuff. So we don't need that right now. But I don't see a way to disable the logs, that specific log. Disable on DTS, disable the TV without haze. So interactive debug mode and track histogram of PCs. No, there's no way. That's a shame. I cannot disable that. It seems like they enable it by default, but I don't want to. No, there's no other way. Okay, so this one is going to have it is going to generate this executable here, and don't be mistaken. This is built with Verilator. That means that it's going to always give us an executable. Actually, most of the simulators give an executable or maybe a script on an executable that a simulator is going to run. So in this case, the simulator is your computer by itself with the libraries of Verilator, and the whole system is made in C, so it can interact with the host to search any files and maybe do some kind of stuff inside of the processor. That's how this works. So you can just run like this in the same way as the ISA simulator. So you can just go to OPT, RISC-V 64, GC, target, that thing, ISA, and RISC-V, what? RV64 UI, for example, and it's going to run there, and that means that that the simulation is done and everything was correct. Actually, if you don't put if you put a program that doesn't end, it's going to be there until the program says that you need to shut down. So this program here means that via HTIF, that weird two variable thing, is going to communicate to the host that yes, this program is able to stop. If you run it just like that, it's not going to happen anything, because you need to always put a process there. There's no other way. So you need always a program to run there, and the way that the program runs is that it loads into the memory and that kind of stuff. We are going to explain all of that, but yeah, this was the test. Actually, I think I'm finished here, and this is a very stupid, very basic tutorial about how to how at least to set up your chip, your stuff. We were capable of running the simulator. We were capable of doing at least one program. I mean, it was a series of programs that it was the RISC-V test. That it just, as you know, well, as I explained before, it's just a collection of tests that the ISA has to test itself. So it's just a program. Like, for example, if you want to test the add instruction, it goes 1 + 1 and expect that the result is 2. That's for every instruction. It has a self-test one for each one of the instructions. So that's why there's a lot of programs there. We run the add one in both the ISA simulator and the simulator from the chip you're running, Rocket chip, because that is the default of this Verilator target. We can do it also with Boom, but it's going to take more time. And that's pretty much it. So if people is interested in this kind of content, I'm going to continue doing it. I mean, I'm going to do it until we have a microcontroller that we can properly manipulate. And I'm going to put this upstream in my GitHub someday. And yeah, I'm going to do the next one maybe in the next week, if I don't have a lot of troubles, because actually graduating from PhD is bollocks. It's very heavy to do it. There's a lot of things to do, and you need to be worthy enough to be a PhD. I don't know. People like me likes to kill themselves with stupid things. So yeah, that's pretty much it. So I'm going to leave you here, and thank you very much for this lesson. So bye bye.